Hi everyone, welcome to another topic in ChemE 122, and this time we are going to be discussing power production from different cycles. And for the first part, we'll now be discussing power production cycles using steam as our working fluid. Recall from our previous discussions that for any power cycle or any work producing cycle, is that the Carnot cycle or the Carnot engine has the highest possible thermal efficiency for any cycle operating between two temperatures. Okay, so first let us try to investigate if we can run the Carnot cycle using steam as our working fluid. Okay, so if you take a look at our Carnot cycle inside the TS diagram for a two-phase system, okay, if you place our Carnot cycle inside the phase envelope, it should look something like this. Now, your steps 1 to 2 and 3 to 4, which are your reversible isothermal expansion and reversible isothermal compression respectively. Okay, these two processes, 1 to 2 and 3 to 4, can actually be approximated in real life, okay, since we have boilers and condensers. And boilers and condensers operate at constant temperature and constant pressure kung purely phase change process lang yung nangyayari. Okay? However, a limitation of this cycle is that if you operate it within the two-phase system, okay, your operating temperature of the cycle is below the critical point. And the critical point of water, this is around 370 degrees Celsius, okay? So, malilimit talaga yung operating temperature natin, okay? Therefore, and we know that the thermal efficiency of a Carnot cycle is equal to 1 minus Tc over Th. So to increase the thermal efficiency, we want to increase the working temperature of the higher temperature in our cycle. So para gawin to, okay, kailangan mo siyang taasan. Pero kung nasa loob ng phase envelope, hindi mo siya matataasan as much. Okay, so malilimit ka ng higher temperature to be below 370 degrees Celsius. So, one way to counteract that is, kung tinaas mo naman, okay, itong Carnot cycle dito, let's say if you draw it here, okay, difficult na i-operate si 1 to 2 and 3 to 4 in single phase operation kasi hindi na siya purely phase change, so mahirap i-approximate yung perfectly isothermal process. You need to have a well-designed heat exchanger for that to maintain na perfectly isothermal yung buong process na 1 to 2 and 3 to 4. Okay, now step 2 to 3, this is your reversible adiabatic expansion, and 2 to 3 can be approximated again by a turbine. Okay, if you have a well-designed turbine, you can really approximate isentropic expansion. However, the challenge here is, as you can see, from state 2, which is purely saturated vapor, tapos state 3, meron tayong ngayon na mixture. And this mixture, this has a lot of low steam quality kasi medyo, ano, tignan nyo, ayan, malayo na siya from the saturated vapor line. Okay, this will now present challenges in the operation of our rotating equipment, especially for turbines. And for turbines, typically the limit is only minimum 90% steam quality. Anything below that will present some erosion, okay, and equipment damage risks to our turbine. So with this, malilimit pa ulit yung operation natin ng Carnot cycle, okay? So hindi tayo pwede bumaba sa 90% steam quality. So siguro, kung 90% steam quality, banda dito lang yan. Okay, by approximation. However, tinaasan mo yung lower temperature ng Carnot cycle, bababa yung thermal efficiency natin ngayon. So, meron siyang drawback pag gusto mong iangat para maging 90%. Okay? And lastly, for step 4 to 1, a reversible adiabatic compression, okay, you can approximate adiabatic compression in well-designed compressors. However, for compressors, okay, compressors dapat purely vapor lang yan or gas phase yung working fluid natin. Tapos kapag pumps, dapat liquids lang. And these are two of our equipment that can pressurize fluids or that can transform one fluid from higher pressure to a lower pressure. So in this case, for reversible adiabatic compression, these two compressing equipment, okay, cannot be used kasi dapat either pure liquid lang kung pump or pure liquid lang kung vapor or gas. So this step 4 to 1 is highly impractical and difficult to achieve, okay, in normal operation. Again, as I've mentioned earlier, if you want to increase the thermal efficiency of your Carnot cycle, pwede mo nga siyang iangat to something like this. Okay, however, difficult na tong operation ni 1 to 2 kasi mangyayari dyan, hindi na siya maging perfectly isothermal kasi difficult to achieve na to, yung perfectly isothermal kung hindi purely phase change yung process natin. Okay, and the compression steps will now occur at much higher pressures. Okay, so with this, the Carnot cycle is not the practical cycle for vapor power production cycles. So now the basic power production model or cycle that we have is called our ideal Rankine cycle. And the ideal Rankine cycle, okay, changes a bit from the Carnot cycle. Okay, we still have the two isentropic steps, the isentropic compression, but this time in a pump. Okay, kasi mas mura ang energy na kailangan mo gamitin for pumps compared to compressors. Okay, and then you can also still have the isentropic expansion in a turbine. However, instead of two constant temperature steps, we now have two constant pressure steps. You have your constant pressure heat addition in a boiler and a constant pressure heat rejection in a condenser. Okay, so our steps here is isentropic compression from a saturated liquid to a subcooled liquid, step 1 to 2. Then step 2, okay, constant pressure heat addition in a boiler, 2 to 3. Okay, ayan. Okay, and then you now have a superheated steam, typically at state 3. You now undergo constant pressure, isentropic expansion rather in a turbine. Okay, to a state na pwede siyang saturated vapor or steam of a higher quality. Okay, and then from 4 to 1, constant pressure heat rejection. Okay, so diba, pag phase change meron tayo in a condenser, constant temperature din yan. So it's easier to achieve constant pressure processes in your boilers and even your heat exchangers as compared to constant temperature processes. So with this, the Rankine cycle is now more practical. So this is now our practical model for vapor power production cycles. Okay, so now some typical assumptions for your ideal Rankine cycle. Okay, so first in our condenser, okay, so state 1 is typically a saturated liquid unless otherwise stated. Okay, so for the ideal Rankine cycle, saturated liquid C, state 1. Okay, you're operating between two pressures. So ibig sabihin na to, P2 is equal to P3 and P4 is equal to P1. Okay, so constant pressure heat rejection sa condenser 4 to 1 and constant pressure heat addition sa boiler 2 to 3. Okay, and last, you have an isentropic expansion in your turbine. Okay, therefore, S3 should be equal to S4 prime. Okay, so prime indicates na isentropic yung expansion process natin. So isentropic state C, state 4. And this is true kapag ideal yung Rankine cycle natin. And even if hindi ideal, if meron tayong inefficiencies, isentropic efficiencies na i-account, okay, you can still use the concept of isentropic efficiencies, okay, using the S4 prime and actual S4 to determine the actual state kung non-ideal na yung Rankine cycle natin. Okay, so let's now have our first example for our ideal Rankine cycle. So we have steam which enters a turbine at 3 megapascals and 350 degrees Celsius and is condensed in a condenser at a pressure of 75 kPa. With this, determine the thermal efficiency of this cycle. Okay, so the first step lagi when you're solving steam power cycles, okay, is to draw your state table. So integrate nyo lahat dyan, temperature, pressure, state, and specific enthalpy and the specific entropy, okay, for each state in your cycle. And then from here, label nyo kung ano yung mga known values based on the given itself. And again, for an ideal Rankine cycle, you're operating between two pressures. So unahin natin yung pressure ni, okay, 75 kPa, okay, 1 to 4, 1 and 4, and 3,000 kPa for 2 and 3, okay. And from here, syempre, given yung temperature, state 3. Ayan. Alright, next. Okay. Si temperature naman ni state 1 or the state of state 1 should be known na saturated liquid. Since ideal Rankine cycle, known na yan. Now for step 1 to 2, okay, 1 to 2 is a pump. And from here, pumps, negligible yung or not appreciable yung temperature difference. Okay, so approximately equal yung temperature ni 1 and ni 2. Okay, so with this, we know that state 2 should be a subcooled liquid. Okay, and state 3, okay, is syempre a superheated vapor. So with this, alam natin yung specific enthalpy ni state 1 kasi alam natin yung fully defined yung state niya. And alam na rin natin si state 3, okay, kasi fully defined yung state niya. And we can now approximate, syempre, na isentropic expansion si 3 to 4. So with this, alam natin na yung specific entropy ngayon ni state 4. Okay, so from this, let us now try to calculate or determine the state of state 4, okay, using the isentropic expansion step. And for state 4, we know that S4 is equal to S3, or S4 prime is equal to S3. And if you take a look at your steam table now, so take your steam tables out, okay, and then take a look, you should now see that the specific entropy na 6.745 lies between the saturated liquid and vapor entropy at 75 kPa. Okay? Meaning, we now have a mixture of saturated liquid and saturated vapor. So, meron tayong mixture, steam quality mixture dito. Okay? And from here, you can now obtain the quality of your mixture. Okay? So, using the mixing formula, you can now get quality of state 4, which is the following. Okay? And from this, you can now obtain the specific enthalpy of state 4 as follows. Ayan. So again, for succeeding exercises, take your steam tables out and try to calculate the values that are being shown in this video. Okay, so with this, we can now update our table, fill out the specific enthalpy of state 4, okay, temperature of state 4, which is saturated saturation temperature at 75 kPa, and the state, which is at 88.61% vapor quality. Okay, so tapos na tayo sa pagkuha ng state 4. Okay, let's now proceed to state 2. And for state 2, okay, the process from state 1 to 2 is a pumping process, and we approximate that process to be purely pressure change only. Okay, so in most cases, you don't need to determine the specific entropy of state 2 kasi but for more accurate solutions, actually, you need to take a look at a compressed liquid table. However, we won't be doing that. Okay, kasi approximate na natin yung enthalpy change. So, hindi magiging maganda yung approximation natin for entropy change. And we approximate the enthalpy change for pumps to be as a function of the pressure change only. Kasi naman, hindi mataas, hindi appreciable yung temperature change for pumps, which is actually observed in real life as well. Okay, so energy balance natin for pumps, okay, delta H is equal to, okay, simply a function of the pressure change, so V delta P. Now, ano tong volume na to? Okay, nagagamitan natin, this should be the volume at the temperature na 91.76 degrees Celsius. Okay, so since approximately equal in temperature nila, constant na si specific volume. So with this, to get H2, we need to first determine the specific volume of state 1. So, tip lagi, if you see any saturated liquid na sa inyong steam power cycle, okay, kunin nyo na rin agad yung specific volume na lahat na saturated liquid. Okay, so you can add that to your table as well. Okay, or if not, just take note of all the saturated liquid specific volumes that you will encounter. Okay, and if you now look at your steam table, okay, the specific volume at state 1 at saturated liquid at 75 kPa or 91.76 degrees Celsius should be the following value, and this is approximately equal now to V2. Okay, so again, specific volumes of state 1 and state 2 are practically identical since we assume the fluid is incompressible. Okay, and the temperature increase in the pump should also be insignificant in value. So with this, we can now calculate delta H. Okay, H2 minus H1 is equal to V delta P. And you can now obtain that H2 is now equal to 387.47 kilojoules per kilogram. And again, you no need to calculate this or determine the entropy for the pump since we only approximated the enthalpy change. And the enthalpy change is now a reasonable approximation. Okay? However, for the entropy change, kailangan talaga natin yung change in temperature so hindi siya magiging ganun ka-accurate yung estimation natin. And we don't even need to actually calculate the entropy change for this cycle or for this state 2 as well. And now that we're done with obtaining all the required enthalpy, okay, specific enthalpies of all states or of all streams in our cycle, let's now proceed to our energy balance calculation. And the thermal efficiency again of our cycle is defined as the network absolute value divided by the steam rate of heat input or QH, okay, which is also equal to 1 minus absolute value of QC over QH. Okay, the absolute value indicates kasi, diba, W net should be negative kasi work producing to, and QC is negative kasi palabas siya ng condenser. Okay, so syempre the network is equal to the work produced by the turbine plus the work required by our pump. Okay, and that's significantly much less yung work ni pump compared sa work output ni turbine. Okay? Rate of heat removal, okay, or QC, syempre from your energy balance of condenser, which is H1 minus H4, and QH is now equal to H3 minus H2. Okay? So you can now obtain the following values from your determined specific enthalpies dito sa table. Okay, and you can now calculate the thermal efficiency of this simple Rankine cycle, which is 26.02%. So far, yung sa mga calculations natin, we take a basis of calculation of 1 kilogram of steam. Okay, yung nag-flow around our cycle. Okay, so for example, given tayo, the network of our actual turbine is, or of cycle rather, is 1000 kilowatts. To get the mass flow rate of steam, this is simply equal to, okay, the network, okay, which is 1000 kilowatts, divided by the specific network, which is usually in kilojoules per kilogram. And from here, you can now get kilograms per second na mass flow rate. Okay, so this is one way to obtain the actual or required mass flow rate of our steam flowing throughout our cycle. Okay. Now, some other possible deviations in our ideal Rankine cycle, okay, you can actually have some pressure drops along your condenser and boiler, although these have to be explicitly stated. Okay, you can also have some heat or system losses using from your pipes or your other equipment, especially your boiler and condenser as well. And you can have irreversibilities in your pump and your turbine. And most importantly, the irreversibilities in your turbines are the most significant. Okay, yeah, take note you have your isentropic efficiencies. Okay, and even a less than 100%, like 90% lang, yung isentropic efficiency ng turbine natin, that has now a pronounced effect on the overall efficiency of our overall steam power cycle. So let's now consider the same example as before, but this time, meron tayong isentropic efficiency ng turbine which is now 75%. Okay, so mag-iiba lang yung state 4 natin, turbine. Okay, so we have to figure out the actual new enthalpy and entropy, and maybe even the temperature. Okay, baka mag-iba yan. Okay, so with this, only state 4 should change since state 3 to 4 or process 3 to 4 lang mag-iba. Okay, so yung outlet ng the turbine yung mag-iiba, the rest should still remain the same. So our previous calculations for state 1 should still hold true, and same for state 2 and state 3. Okay. So only state 4 should change since non-isentropic na yung process natin. Okay, so we can still use, okay, the isentropic state 4, which is S4 prime is equal to S3. Okay, same pa rin as our previous calculations. Okay, so same pa rin yan. Okay, and we will now use the definition of your isentropic efficiency and your isentropic state, okay, to get the actual state of state 4. Okay, using the definition of your isentropic efficiency, recall from our previous lecture again. Okay, ito yung definition ng isentropic efficiency of a turbine. And we can now get the actual H4. Okay, so we can get the actual H4 to be the following value, 2581.23 kilojoules per kilogram. And if we take a look again at our steam table, okay, this specific enthalpy is still between the saturated vapor and saturated liquid specific enthalpy at 75 kPa, meaning we still have a mixture, okay, of vapor and liquid at state 4, and we can still get now the actual quality and specific entropy if you still want to calculate it, just to prove na nag-increase nga yung entropy natin. Okay, so with this, you can get H4, which, okay, or X4 rather, to be 96.44%. Okay, so now our actual turbine outlet state has an increased steam quality, okay, which is 96.44%. Okay, and specific entropy should also now be the following value. Okay, so same pa rin ang definitions natin ng thermal efficiencies. Okay, mag-iiba lang ng values yung CW net and QC since nag-iba yung value ni H4. So recalculating for the new values of the network, okay, the heat removal and the rate of heat addition, okay, you can now get a new thermal efficiency which is now 19.49%. Okay, so with this, naging 75% efficient na lang yung turbine natin, ang laki na din-decrease sa ating overall thermal efficiency ng cycle natin. Okay, so now, how do we further increase the thermal efficiency of our Rankine cycle? Okay, so can still base this on the principles of our Carnot cycle. Okay, to increase the thermal efficiency, you can either increase the temperature of your heat addition step, okay, increase the temperature at which heat is transferred from the working fluid to the boiler, or you can also decrease the temperature of your heat rejection step, so dun sa condenser natin. And there are other ways to achieve this, okay, by manipulating process variables in our ideal Rankine cycle. Okay, so one way for us to decrease the working temperature of our condenser, okay, is of course to lower either the turbine outlet pressure or lower the condenser inlet pressure. So babaan natin yung working pressure ng condenser natin. Okay, and as you can see, based on the TS diagram, the overall, okay, area encompassed by the cycle is proportional to the network of our cycle. So to increase the area, babaan natin yung lower boundary to a lower pressure and thus a lower temperature. So with this, if you lower the turbine outlet or condenser inlet pressure, tataas yung thermal efficiency dapat natin since we can now have an increase in the network. Okay, another way, okay, is for us to increase, okay, the working temperature of our turbine and or the working temperature of our boiler. So we can superheat our steam further to much higher temperatures. So i-adjust nga natin yung overall area, pero to the right natin siya i-extend. So lalaki by this amount. Okay, yung network na pwede natin reproduce from our cycle. Okay, so another way again for us to increase the thermal efficiency is to increase the network by increasing the thermal operation or increasing the temperature of our boiler and the turbine inlet. And another way for us to increase the thermal efficiency is for us to increase the boiler pressure. Okay, tataasan natin ulit yung network or yung area by moving the area of the whole process pataas, pero meron tayong cut off to the right. Okay, pero the net effect of this should still be an increase in the network and an increase in the efficiency of our cycle. So again, to increase the thermal efficiency, okay, you can decrease the pressure of your condenser, you can increase the temperature of your boiler, okay, or you can increase the pressure of your boiler as well. So these are three ways for us to increase the thermal efficiency of our cycle. Okay, so to illustrate the first scenario, let us go back again to our original problem. Okay, isentropic na ulit. Okay, ideal Rankine cycle. But this time, the condenser pressure is now 10 kPa instead of 75 kPa. Okay, so for this, let us now get a new working, okay, conditions for state 4. We need to know the actual state, okay, and the new specific enthalpy. Pero state 1 should still be a saturated liquid. Okay, so that will still hold true. So let's repeat the calculations, but this time 10 kPa na si condenser pressure. So again, state 4 is from isentropic expansion from state 3. Okay, so you can see from a saturated steam table at 10 kPa that the specific entropy still lies between, okay, 10 kPa and between saturated liquid and vapor entropy. And as you saw from the previous TS diagram, dapat makakuha tayo ng decrease in the nth quality of our steam. Okay, papalabas ng state 4. Okay, so calculating the actual or the isentropic state of state 4, you can get the steam quality at state 4 to be 81.28%. Ayan, you can now again calculate the specific enthalpy at state 4 to be 2136.10 kilojoules per kilogram. And similarly to the first scenario, to get state 2, okay, we still assume na incompressible fluid, negligible change in temperature, kaya approximately equal pa rin yung dalawang temperature ni 1 and 2. Okay, so the enthalpy change from state 1 to state 2 is simply equal to V delta P, where V is a specific enthalpy or specific volume rather at 10 kPa or 45.81 degrees Celsius. So to calculate H2, assume V1 is approximately equal to V2, and let's get V1 from the saturated liquid table, and V1 is 0.001010 meter cube per kilogram, which is approximately equal to V2 now. And from here, okay, H2 minus H1, which is the delta H of your pump, is equal to V delta P, and you can now calculate H2, which is 194.83 kilojoules per kilogram. Okay, now that we have filled out our table, okay, let us now determine the thermal efficiency of our cycle. Okay, so from here, just plug in again the values, so same pa rin definition. You can now get the network QC and QH, and the thermal efficiency of our cycle now is now 33.44%. So kanina, nung 75 kPa, okay, 75 kPa yan, 26% thermal efficiency natin. Nung ginawa ng 10 kPa, this is now 33.44%. So, ang laki nung pronounced increase ng thermal efficiency ng cycle natin. Just by decreasing the condenser pressure. Okay, so now in your worksheets, okay, you have the other variations of this cycle. Okay, where you can vary either the temperature of your boiler or the pressure of your boiler, and another scenario where you combine all of these changes. Okay, so please do that in your worksheets, okay, before proceeding to the next part of the lecture, which is now the modifications to our actual Rankine cycle. So with that, that's it for the ideal Rankine cycle, and thank you for listening.